This is my Lab 1 for Physics 1. So the table of contents is the introduction of the principles and formulas used, the system and the surroundings, the explanation of the experiment, the video, the explanation of the code, the similarities and differences between the data and model prediction in terms of fundamental principles of physics, possible sources of error and how to prevent them, and discussion and conclusion. So to introduce this lab, firstly, the purpose of the lab is to measure the constant velocity by calculating the change in position over a certain time interval, and compare the results of the computational model and the ones from the graph produced in Tracker from the video used to depict the motion of the marker. For assumptions, in the model we assume air resistance and friction are negligible, and that there's no movement in the other axis except for the x-axis. And a brief preview of the main result is that the two models appear to be similar in the beginning but deviate as time goes on. The key concepts, so firstly we have Newton's first law, which states that the present state of motion and absence of net interactions or forces on the object. As there is constant velocity, we apply Newton's first law that states that the net force upon a system is zero and that there is constant velocity. For Newton's second law, it states that the net force acting on a system is equal to the product of the acceleration and the object's mass as long as the mass is unchanged. And below I have the velocity update formula and the position update formula, which I will be applying in this lab. And when it comes to the system and free body diagrams, the system is the marker and the surroundings is the surface of the table, the air, etc. In the initial conditions, we have the normal force and the gravitational force which cancel each other out, as well as the force applied on the marker by the person, causing there to be a non-zero net force, which means the marker accelerates due to the force applied by the person. And in the final condition, the net force is zero because the marker is moving with constant velocity. The experiment basically included a pen or a marker with a circular shape being rolled on the surface, with an initial force being applied. The pen moves with constant velocity, and in Tracker, the pen is depicted to be in the center, and the video of its motion tracks the velocity by crafting a graph of position versus time. The relationship is expected to be linear if we follow the assumptions mentioned in the introduction. For the results, I found the initial time, the initial position, the final position, which allowed me to calculate delta T and delta R. I know that the mass is 1 kilograms, so the average velocity would be delta R over delta T, which ended up being 0.2228 meters per second. As was previously discussed, as there is constant velocity, this means the initial and final velocities are the same. When it comes to the code, we plug in the initial and final position, the mass of the marker, the average velocity, and the time interval. We also set the initial conditions and loop for time until it reaches the last time step, and therefore allowing us to use Newton's second law. I put a screenshot of the code from CloseScript and also the link. Now, when it comes to the actual and the predicted graphs, these are the two graphs that I got, with the blue dots showing the experimental or tracker and the orange dots showing the computational model that I got from my code. When it comes to discussion, both graphs were linear, meaning the velocity is constant throughout. Initially, the speed of the predicted marker and the observed marker are very similar, which is expected for a model based on a net force being applied to the object, but the speeds and velocities begin to diverge towards the end of the change in time range. When it comes to discussing some errors, there could have been slight differences in placing the center of the mass of the marker in Tracker, which affects the position. The model also does not account for any motion in other directions, which impacts position, and the existence of more axes and not just the x-axis, as we do not take any others into consideration, and the process of rounding numbers and doing calculations could create deviations in the final result. For further discussion, in the beginning, the two velocities were similar, and we see that the slope is linear, meaning the velocity is constant and net force is zero. However, as time passes, the difference between the computational model and the tracker increases too. A force acts on the marker because friction and air resistance exist, something the computational model does not take into account, meaning the net force becomes non-zero and the velocity is non-constant, aligning with Newton's second law. For further questions, we could ask, what if the axes were flipped? If the axes were flipped, the slope would not change in magnitude, but only become negative and in direction and appear to be pointing downwards. This means that the velocity is constant. Even though there are forces acting on the system and we cannot detect them, they cancel each other out, so the net force is zero. And this is the end of my Lab 1 for physics.